In this video, I'm going to start talking about some solid state physics. And so it's looking at quantum mechanics and how that's applied to solids. And so there are several ways you can model this. And in this video, I'm going to be talking about what's called the free electron gas. And so we can think about this as like a three-dimensional infinite square well. So remember, our infinite square well looked like this, where on the outside the potential was equal to infinity, where on the inside the potential was equal to zero. But now we're going to be doing this instead of in one dimension, we're going to be doing it in three dimensions. And so you can think of maybe like a cube. So if we have a cube here, where everything inside the cube is v equals 0, where everything outside the cube is v equals infinity. And so we're sort of modeling like a piece of material this way. So if you have, like a cubic piece of like a metal or something, you can sort of think about the metal, the solid metal, as being sort of like a box or a container for the electrons, which can sort of move freely about on the inside. So in future videos, we'll be looking at more precise ones where, because if you have a solid like this, then you have nuclei in it, and they're sort of spaced evenly apart in three dimensions like this. And so you have these evenly spaced regular sort of potentials inside. And so we would actually have to not just say that the potential is 0 everywhere inside, but we're going to sort of build up to there. And actually, in the future, probably when I'm done with this Griffith's book stuff, I'm actually going to do a playlist on materials modeling using density functional theory. And so, this is a little bit of a prelude to that. So this free electron gas is kind of the easiest and probably most inexact way to model it, but it will introduce us to several concepts that will be important for us later on, even though this model is not very precise. But neither was the one-dimensional infinite square well, but that was kind of our starting point for quantum mechanics. And so this essentially means that our potential, which is this, is, like I said, 0 when it's inside. And so we can think of this box, if we sort of put this with an origin right there, then if we say that this is the length in the z direction, and this is the length in the x direction, and of course there would be sort of inside here like this, we would then have our length in the y direction. I guess that should be an L in the y direction. And so that's what this means. So going from 0 to Lx, going from 0 to Ly, going from 0 to Lz, the potential is 0 and is infinite otherwise. So the Schrodinger equation we can separate into three variables like this, one for each direction. And so we end up with these. We have our E equal to the total energy equal to the energy of the x, y, and z directions. We rearrange, make these substitutions for k, and k is the thing that I'll be talking about a lot here in a little bit. And so we have general solutions that look like this for the x, the y, and the z direction. We need some boundary conditions, so we need the wave function to be equal to 0 at x, y, and z equals 0. And so it needs to go to 0 at the sides of our potential here. And so that means that the b's here all need to be equal to 0, because cosine of 0 is not 0. And so these b's all need to cancel out these cosines here. And same with at the 0, we also need at the other side of our potential here for the wave function to be equal to 0. And so those are some of the boundary conditions. That means, which means that k must be such that for the given size of the well, it gives integer multiples of pi at the boundaries Lx, Ly, and Lz. And so we end up with this, so k times our Lx is equal to some integer times pi, so on and so forth for each of these, where the n's are going to be integers. We do some rearranging and we get our k's equal to this. We do this normalization, and so I actually went through this normalization in a previous video. And so it's using this normalization that we actually derived there, where it's 2 divided by a, where a is the length in one dimension of one side. And so we're using Lx, Ly, and Lz, so we end up with this 8 over this. So we then put all of our split variables back together into our total wave function, and we end up with this right here as our solution, where this is what the allowed energies are right here. And so the thing to notice here is this part in parentheses, where we know that each of these is our k squared, since we said that the pi n over L is what our k's are equal to. And so this looks kind of like the Pythagorean theorem in 3 dimensions. So, you know, the Pythagorean theorem in 2 dimensions is, you know, the a squared plus b squared equals c squared. In 3 dimensions, it would just be a squared plus b squared plus c squared equals d squared, where then we can say that d is equal to the square root of a squared plus b squared plus c squared. And so this looks kind of like, because we have sort of an a squared, a b squared, and a c squared right there. And so it looks like a line in 3D space, and a line sort of with a direction in 3D space is a vector, and so we will call that the vector k. So for now, k with no subscript. So this vector k has a constant component in the I direction. So what I mean in this description here is, if we have this 3D grid, and say we have our origin right here, this is our z, this will be our x, and then this one back here will be our y. So if we look at something that has a constant x, so then we'll get this, and then when we change sort of the z, the z component, we get this, then this one, going all the way up. Then we can do it again, so we then start changing our y component, and we start moving up, and we sort of sweep through an entire 2-dimensional plane inside of this thing, all for a constant x. Then we can sort of increase x by 1 and do the same, where we sweep through in a constant plane. And so we can sort of build a 3D grid using this right here, by, say, holding this n constant, sweeping through all these ones, putting this one up by 1, sweeping through all these ones, putting this one up by another one, sweeping through all these ones, and sort of doing this iterative method until we fill up an entire 2D plane. Then we can increase this one by 1 and do the same thing over and over again until we end up getting all of the points here in this 3D grid. And so after doing this for all allowed n's, we have produced a 3D grid of points that are a distance of this from the origin. So this is our k here, and this is sort of like our 3-dimensional Pythagorean theorem here. And so we are producing vectors, and then sort of a vector pointing to every spot in our 3D grid. So each point on the grid represents a possible stationary state. for a pair of electrons under solid. So stationary state, meaning that it's a state that won't change in time. And so for every pair of electrons, so every point on this grid is a possible state for electrons in our solid. The electrons, because of the Pauli exclusion principle, there can be 2 electrons for every point in this grid up here. And so I'm saying here also that if these were fermions, they would all collapse down to this ground state right here because they can all occupy the same space. But since we are using fermions, which are spin half and have that antisymmetric spin, we therefore, once we put 2 in this ground state, then we have to put 2 in each of these other states around it. And so doing that and sort of building out from the origin, what we end up doing is making a sphere of all the states. And so you can see there's spin up and spin down in every state here. You can see that one of the electrons, if it's excited, can move outside of this sphere. And then, if it releases a photon, it can fall back into there. But this is representing all of the states that the electrons can take in our solid. And so since one of the k's squared is equal to the negative k squared, we therefore only need to use 1 octant of the sphere. So if you take a sphere, you can sort of divide it in half at the equator, then you can sort of divide that half in half at like I guess if you're thinking about the globe, like the prime meridian, and then you can cut that into quarters, which, a quarter of a half is an eighth, and so you only need an eighth. And so we see our 3D grid in here, and then we have this octant of our circle here. And the reason is because if you kept all those other ones, like I said, the k of something squared is equal to the negative squared, and so you would just be repeating the states over and over again in each octant. And so we just need the 1 octant. And so the volume of each grid cube, which is where our 2 electrons would be, is a function of the volume of the entire object. And so this is, the dimensions of our cube, and so that is just equal to our volume. And so the octant of the sphere has a volume determined by the outermost states, which are the longest k values, and we will define those as k subscript f, which will make sense here in a little while why we put that capital F down there. So the volume of the sphere is given by this formula, and kf, so the vector going from the origin to the outermost shell, so the sort of highest energy states that are occupied. So that kf is our radius, so we just substitute that in for the r. And then we divide by 8, since we're using just an octant of the sphere, we get a volume that is this right here. So the volume of the sphere is determined by the number of atoms and the number of free electrons d, because the number of electrons that an atom in our material has times the number of atoms is going to be sort of the number of states that are taken up. Well, actually, it'll be that number divided by 2 that are the states, since with the spin up and spin down, you can have 2 electrons per each state. And so we get a volume that looks like this. So this is our number of electrons, d, times the number of atoms, d, and then we're dividing by 2 here, and then this is the volume of one of the spaces here. So yeah, this is the volume that each state occupies in the grid, in the nd over 2 is the number of electrons that need to occupy the spaces. If we rearrange it to get kf by itself, we get this. And remember, kf is sort of the vectors that go all the way out to the outermost occupied shell of states there. And so then we just define rho as this nd over v, and so we get this as our kf. And so here I wanted to take a little bit of time to sort of try to get a better understanding of what we're actually doing here, because in the Griffiths book he seems to kind of assume that you already understand what all this like k-space stuff is, and he doesn't really go into time explaining it. And so this is something I've worked with in my research using cryo-electron microscopy, which uses sort of 2D spatial Fourier transforms and things like that. So I wanted to take a little time to explain what this is, to explain what the K and the KF even mean. So remember, we defined our K as this n pi over L for each I equals this, and this was our wave function right here. So we have the K's here in the arguments. And so the number K multiplied by the variable in the argument is telling us something about the frequency. And so if you know your trigonometric functions, if you have like the sine of x, you get something that looks like this. But if you have like the sine of 2x, you get something that has like 2 wavelengths for every 1 wavelength there. So this other number, which is what the K is kind of taking the part of here, is sort of adjusting the frequency of it. And so when we have different Ks, we have different frequencies. And so these Ks, since the argument of a sine function shouldn't have, well, I mean, I guess I shouldn't say shouldn't have, but in this case, we don't have units in the entire argument. Well, x is equal to a length, and so the kx has to be equal to 1 over length. And so these are often, this is often called this k-space, which is actually what Griffith calls it, and you know, that's somewhat standard. So this k-space is sometimes often called reciprocal space, since it has units of 1 over length or 1 over area or 1 over volume. So it's the reciprocal of like what is called real space. You know, so real space is called real space. This is the space we all know and love. You know, the space from me to my door is, you know, some many feet, and that's a real space. But a reciprocal space of it would be 1 over that many feet. And so that's why it's called real space and reciprocal space. And so the vectors k going from the origin to points in k space are called wave vectors and are related to the wavelength by this. And so they are inversely proportional to the wavelength. And as we know, that frequency is is also inversely proportional to the wavelength. We then know that our k is proportional to our frequency. And so we're using angular frequency here, which is, so a frequency is the v, which is the velocity of something divided by the wavelength here, the lambda. Then we just kind of multiply that by 2 pi to get the angular frequency. Therefore, k is related to frequency this way. So k is omega over v. So our angular frequency divided by the velocity of the particle. And so k is directly proportional to v. And since the energy of our particle is directly proportional to the angular angular frequency by this, so angular frequency is equal to our energy divided by h bar. We now know that the k is directly proportional to our energy. And so you can think of the k's as energy. And in fact, we have this, so k equals momentum over h bar, which is just equal to this, which is how we already defined K above. And so we see that K has this energy here in the numerator. And so you can think of K's as energies. So like I said, the point being K is proportional to energy. So the different points in K space represent different energy levels in our material here. And so this is our allowed energies here, which then we turn each of these into their K. Then we sort of multiply both sides by 2m, divide both sides by h bar squared. We get this. We take the square root of both sides. We've already defined our K as this because this is just the Pythagorean theorem in 3D space. And so we end up getting this, which is our K is equal to our 2me, square root of 2me over h bar. And so, yeah, like I said, we can think of this K, and I've even put it here in vector form with a little arrow over it. We can think of it as a vector where the magnitude of the K is the energy. So that represents the energy, where KF, this K with the subscript big F, which I said was the sort of longest, the highest magnitude vectors in this space. They go all the way out to the highest occupied states. That is called the Fermi surface, which corresponds to the Fermi energy. And so that F there is to tell us that we're talking about the Fermi surface. And so these, which I just copied from Wikipedia. So the Fermi surface separates occupied and unoccupied electron states at absolute zero. And so that's, I guess, another assumption I should have made explicit. When we're talking about this, we're talking about at absolute zero. And so, you know, when you're studying like solid state physics, one of the things you're doing is looking at, you know, how like a change in temperature and things like that actually change sort of the surface of this sphere up here. So at absolute zero, where there's no like thermal energy or anything, you'll get this nice sphere like this. But if you start adding energy, it's going to affect the surface of the sphere as electrons, as is shown here, sort of get bumped up or promoted to higher energy states. And so, you know, that's kind of the reason why people who study solid state physics bother doing, you know, all this K-space stuff, is because you can learn about the material by looking at like the surface of your object in K-space. And so that's, you know, this is kind of the when I said before that this is not a very good approximation, but it introduces us to some important concepts. This is kind of the concept that is important for us to understand, is this idea of K-space. And so, yeah, the Fermi surface is the surface of our sphere when the electron states are at absolute zero. And the Fermi energy is the energy difference between the highest and lowest occupied single particle states in a quantum system of non-interacting fermions at absolute zero. And so the take-home message here, the magnitude of these vectors represents the energy of the particles in those states. Then we can think of the angles. So, you know, the vector has magnitude and direction. So you can think of the direction as representing the phase velocity, which in an isotopic material, like, you know, just like a pure metal or something, the phase velocity is just the direction of wave propagation, which is also the direction of energy flow. And so you can think about it as just the direction that a particle with such and such energy would be moving. And so that is sort of the clarification of all this K-space stuff. And so now if we get back to what Griffiths was talking about. So free electrons in our box, which would be like our material, can be thought of as an electron gas, they are free within the material constraint only by the boundaries where the potential energy is infinity, are those that are on the very surface of the sphere octants. And so those are the ones that, are going to get promoted up first and then be able to sort of move about the material freely. So in other words, those with energy corresponding to the KF are the ones that are going to be moving about the material freely. And so using this and this from before, we get as our Fermi energy here being equal to this h bar over 2m and this 3 pi squared rho. Remember, the rho is the n times d over v, which was the sort of number of electrons divided by sort of the unit volume for each state. So to get the total energy, we first want to look at thin shells of each energy level of our sphere. So sort of like the layers of an onion. We want to look at the energy at each layer. And so each layer we can think of as being, extremely thin. So this differential K. So, I mean, this shows it as pretty thick just so you can actually see it. But we want to think about this differential K. So shells of our sphere octant that are the thickness of that differential K. So the formula for the area of a surface is 4 pi r squared. Our r is going to be equal to k, because the k's are the vectors pointing out to that shell of the sphere. So to get the volume of a shell with thickness dk for just 1/8 of the sphere, which is why we're dividing by 1/8, we will use this. So we have our 4 pi k squared, which is the area of the surface of the sphere, times the thickness of that shell. So this 4 gets canceled out, this 8 becomes a 2, so we get this 1/2 pi k squared dk. And since there are 2 electrons per state, one spin up, one spin down, and each state takes a volume of this from above, we therefore have as the number of electron states per shell as being equal to this. So the 2 in green here is because there's a spin up and spin down per state. This right here in red is the sort of surface or thickness of the surface of our shell, and then this is the volume that each state takes, and so we end up with this right here. And so where the total energy in a single shell is the product of the energy state per shell, which is this, with the number of energy states in a shell, which is the thing that we just got. So we just multiply those two things and we get this as the energy. So the dE, it's the differential energy of energy. So the energy in just a single shell on our sphere, or an octant of the sphere. And then so to get the total energy, we actually have to add up every shell, from the origin all the way out to the KF, which is why we go from 0 to KF. So we're doing an integral, which is just a continuous summation of our K to the fourth here, because we have K squared times this K squared, which gives us K to the fourth. After we evaluate this integral, we end up with this as our total energy. And so then the reason that this is called an electron gas, or sometimes a Fermi gas, is because it exerts a pressure sort of like a gas. So what we see is that there is this 1 over v to the 2/3 power factor, which is inversely proportional to the energy. So we have this down here. The energy and the volume are inversely proportional, which means that the total energy is dependent on the volume of the box the electrons are inside. And so if the box expands, then we see that the energy goes down, since energy is inversely proportional to the volume of the box. And the energy decrease that we will see with respect to some infinitesimal change in the volume is this. And so we just take the derivative of this, which gives us, which takes the 2/3 or the minus 2/3 from our v and sort of brings that out front here and reduces this by -1, which is why we have this -5/3 now. But this part here in red is just equal to the E total, and so we can then just do -2/3 times E total over V. And so this is the change in energy with some change in the volume. So if you increase the volume by some small amount, you decrease the energy by this amount. And this can be seen to do work in the same way that the pressure of a gas does. So P is equal to pressure. And so I'm not going to go through all the numbers on here, but we see that there is a pressure here. And this is what is known as the degeneracy pressure. So if you're into, like popular science stuff, you've probably heard about neutron stars and how those sort of prevent themselves from collapsing because of this degeneracy pressure. Well, this is the degeneracy pressure that we're talking about here. And so the electrons are sort of pushing outward and sort of keeping the thing from collapsing in on itself. And this is also what keeps, anything that is, sufficiently cold, something that's like close to absolute zero from completely collapsing, because we don't have the material just sort of compacting down, because it has this sort of pressure pushing outward. And so this pressure is not electron repulsion. It's not thermal motion, since in this analysis here we have ignored both of those. But it is a purely quantum mechanical effect. And yeah, anyway, again, as usual, the lecture notes will be linked to in the description down below if you wanted to look at this stuff in a little bit more detail on your own. But I hope you found this video helpful in understanding, well, this is sort of first step towards understanding like solid state physics. But anyway, I will see you in the next video.